wrong. Okay, so one of the reasons why I'm holding the session is that one of the core aspects, of course, is networking, and I still haven't quite gotten there where I wanted to. But since you need to have a proper understanding of networking as a result of this course anyway, but also for the next task that you'll be doing, at least in the second assignment, and most definitely in the project as well. So, and we still didn't talk about some elements of networking yet. But before getting there, what did we talk about last session? Does anyone recall? Just to
package sniffing.
Pardon?
Package sniffing.
Packet sniffing. Okay. So the exercise was meaningful. Okay, that's good. That's me. Did anyone do it actually? Because it was a bit tight in the end. Did anyone do it at home? Because I gave you the trace, so you could have done it. Okay, interesting. So you guys are not really keen networking, are you? Huh?
I did the Wi-Fi exercise.
Yeah. Okay. That's good. Yeah. You figured it out in like 5 seconds, right? That's not necessarily helpful for the rest of the class, though. But it's good. So, but I still encourage you to have a look at it because I think it helps you a lot to understand the layers a lot better. At least from a practical level, you see, okay, why do we have those different layers? Because there was a lot of talk about 4 different headers, I believe, right? Or I think at least 3 we talked about, and that makes things quite confusing at times, I guess. And I understand it because if you condense that into a 1.5 hours lecture, that's a bit too much actually. Usually it's supposed to have a course on that thing. So, but that's what this course is about. We're jumping on a lot of topics, and you guys are supposed to kind of pick it up because we expect you to be old enough now. So that's your, hang on, 3rd or 4th semester? 4th, right? 3rd?
This is the 3rd.
Yeah, cool, perfect. So, right, first year's over. All the mandatory, okay, of course there are exceptions. This course is always full of exceptions, but the mainstream is usually 3rd semester, right? Yeah. Okay, coming back to networking. What in networking did we talk about apart from packet tracing, apparently, which I now know? Yep.
We did TCP and UDP.
Yeah.
We also went over MAC addresses.
Yeah.
And it's hard to have in the OS I layer.
Yeah.
Layers, yeah.
That's right. And that brings me to my next question, because your point is good, because you mentioned all the different components which are relevant. But what was this ISO OSI layer model thing? I have no clue, so I need to ask you now. So, does anyone recall at least what it's about? And then start with some layers, and we get them by collective intelligence. We get them back together. I think all of them. How many were there? Let's start with that. Be daring.
8.
8? Okay, that's interesting. Okay, there must have been one added since we talked last time. Anyway, it happens, those standards change very quickly. Now, I think it's, any other voices? I'm still more on the 7 side, but I'm always open because standards really change quickly. No, it's 7. So, why do we have seven kind of layers? What the heck is that about? Why do we have a layered model to do networking? Why don't we just, send stuff in one giant packet? Everything's in there. Please.
To actually figure out what we're sending and receiving.
Yeah. Yeah, that's sensible. Yep.
Yeah, because how computer is built up, just like how does it turn like all the electrical signals into something understandable for a human?
That's right. Yep.
That's the machine layer, the OS, and then the applications and everything in between that which I don't remember unfortunately.
Of course. So your point is actually you were currently pointing to the more like an operating system, how a machine is built up, and you're right. The parallels are striking. It's precisely kind of the same problem, right? So if you look at the hardware level, and you have drivers, you have your operating systems, you have your application on top, and if you look at the networking side, which is slightly different layering, it's actually has a fairly similar decomposition. So your point is quite good. We get to that again in a bit more. What is another reason? Why do I use a layered model? That's one reason, but not the only one.
It's important to distinguish between different parts of the communication.
Yeah, yep, that's right. So that's again like breaking down the problem a bit, right? So on the fly, so we receive a package, then we look, okay, which service is related to, so we can do it. Yes, still another point I want to make, because that's why the internet is called the internet.
Protocols and standardization.
standardization.
Yeah. Elaborate, please.
Each layer has its own standard or protocol, so it's universally acceptable if you program to always read one protocol.
Yeah.
Then you can also use it in the next layer by peeling away a protocol in the layer before it.
Yeah, so your point is very good. So by minimizing or concentrating one protocol on a given layer, you minimize the potential for error, right? In specifying a protocol, make it simpler. And extending on this, precisely that idea, what can you do if you decompose everything like this?
You can update one layer or make changes to one and not affect the others, so it's easier to
Precisely.
understand.
I mean, that's precisely the point I want to make, because that's in reality what we are having. So that we get rid of this for a bit, because no one knew, right, when they came up with the TCP/IP layer, how it actually would end up, right? So we have all those layers here. We come back to that. How many layers do we have in the TCP/IP model? The one we discussed first. Okay, that's closer. Yeah, speak up. Four is good. Which ones?
Application.
Yeah.
Application on top, networking or physical at the bottom.
Transport first. So we get there. Yeah, transport. No one can read it, but since you know what I talked about, you remember it. Then network. Network you agree on. Okay. Okay. Yeah, and the last one.
Physical. Physical.
Yeah. Other voices?
In the OC model, it's called data link, but I'm not sure in
Okay.
physical.
Physical. Okay. Right. That's very essential. But I think the most important is network or network access layers is oftentimes used, but it's not consistent. That's the problem with this model. So physical probably get away with this as well. But you mentioned a lot of different layers there, and they're all correct, but they are from a different model. So, but let's just come back to that, to your argument that you made, right? We can exchange different protocols on different layers. And no one knew when they specified this thing in practice, how many protocols would exist on each layer, right? So there were some suggestions, oh yeah, let's put the particular protocol here. Just, let's name some protocols. Which protocols exist on the application layer? Just to get a bit of a feel.
HTTP.
Oh yeah, that could work, yes. Okay. Anything else?
HTTPS.
Oh yeah, that's, yeah, okay. FTP. What is FTP? We didn't talk about this yet?
Transfer protocol.
Yes. You're reminding me we talked about it. Okay. So another protocol?
SMTP.
SMTP. What did that fellow do?
Basis for sending email.
That's right, right? So it's a standard protocol for transmitting emails between mail servers, technically. Anything else? Heaps of stuff, right? Most of the protocols there. Let's go one level lower. What do we know there? TCP, UDP. One level lower. What's there? IP. One level lower. What's here? That's messy.
Ethernet.
Yeah, that's right. Ethernet is there. So it's 802.3 as a standard. You guys know 802.11 as a standard. What is 802.11?
Wi-Fi.
That's Wi-Fi, right? With all these variants, like, you know, A, G, I, and whatever. Cool. Any other standards? WiMAX, exactly, all the mobile stuff. So, okay, cool. So you get the gist, right? So it's all about the connection protocols. But the point is, when over time, it actually boils down, if you look at it, what in terms of the number of protocols that have been specified and changed over time, well, it turns out that this layer, the network layer here, well, sorry, that one here, particular, pretty much boils down to having one protocol and the transport layer having slightly more, right? So there are a few more other protocols on that layer, but it's very minimal. But here is a lot of protocols on the lower level because devices have changed, right? The hardware has changed. Wireless transmissions got a lot faster over time. I mean, you guys just need to follow Wi-Fi, let alone mobile networking, right? 3G, 4G, and now 5G and so on, and all those intermediate technologies, right? They are all in here. So there's a lot of change here. And there's a lot of change, of course, here as well, right? So HTTP is around for some time, but it has changed as well, right? So there's different iterations of the standard, right? And there's far less of that on this level here. We have a bit of movement now with IPv6, right? So, But you know, that's such a slow movement. Does anyone, first of all, what's IPv6 in a nutshell, very briefly?
Something that's supposed to actually be useful for a lot of addresses, because IPv6 was actually just a test case that got standardized in a way.
Mm-hmm. So yeah. So it's about addresses and so on. We're running out of those, so we need to have a new IP protocol. Does anyone know when that was standardized? We get to that protocol in a bit more detail later. Just to give you a bit of a time horizon of how fast things move on the internet.
In the 90s, like 96 or something?
1998, you're right. So this was standardized. That is the successor of the current internet protocol, was standardized in 1998, right? And we're still not quite there adopting it. I think about, what is it, 25% of the major traffic is running this. The rest is still running the old protocol. So things are incredibly slow moving on those layers. It's fairly stable, right? So, and this is the real power of this layer protocol. You can exchange. We don't know what's happening here in 5 years, right? And this can stay stable for the next 30 years, and no one will bother, right? So, and everything will still work. In case you get your next HTTPS implementation wrong, well, your browser will say, can't read it. But your email still work, right? Your FTP connectivity still works, right? DNS will still work, right? So that's the kind of important message here. The layering is about decomposition and also, portability and changeability on different layers, because you guys are mostly working on this layer, and probably mostly thinking on this layer as well, right? Whereas the admin, network admin probably thinks more on those layers. You're probably more on that one than anything else, right? If you're a hardware manufacturer or interested in hardware in general, you probably think more about this layer, right? Or if you're an infrastructure manager, right? So you have a organization, you need to decide what's the next kind of high performance network that we want to use. You're kind of more concerned about changing all network cards on all machines and ensure that it's better as a protocol that is, can interact with IP, right? Else you wouldn't be. So you even find it in the job stratifications that you have in IT, that they're kind of reflected on this layer as well, right? So, and coming back to operating systems, that's kind of similar as well, right? So you have the hardware here, you have something like drivers in between, and then the operating system, and then the applications on top, right? So it's of course slightly different than here, but you're exactly right in the sense that it breaks down what's relevant for a service, right? So when you write your web service application, you technically don't care about the host, which would be on this level, right? You only care about the particular service you're writing for, right? So waiting on port 8080 for requests for your IGC assignment, all alike, right? So it's strictly speaking, you only care about here. Part of the reason is for that is, for example, you're using Heroku, right? And Heroku is precisely about not caring about any of that, right? So you ignore that entirely. So, but we get to that. You of course need to care about it a bit. But this is one of the key points. So that's about the interchangeability. That's the key value I think that the internet was brought about. That's why it worked out so well. There were other competing standards that thought, okay, let's do a layering protocol and specify all the protocols that will ever exist. Yeah, that didn't go well, right? So then you realize, oh, then there's new picture formats, JPEG, PNG. People start transferring MPEG, files, which is, a lot of data for that time anyway. No one anticipated that this stuff would ever need to be transferred via the internet. But of course, with this flexibility, you can quickly adopt new protocols, and it's just a matter of installing a new, browser or whatever else, and suddenly your protocol is supported. So that's one of the aspects there. Right, so we're still at 4 layers, right? And you thought you got away with this. There's the other ISO-OSI model that has a few more layers. So we decided democratically, or did we, that it's 7 layers. So that's pretty good already, right? So that's how you make a standard. You decide on it. All right, which layers are we missing? Or which layers? It's to your own benefit to participate, because you need to know those layers later on.
Presentation layer.
Okay, where's that thing happening? Okay, I remove a bit here so we have a bit more space. Presentation layer, where do you think it is?
At the application.
Somewhere there, right? So let's put it here. Presentation. Okay, what else?
Session.
Session, okay. Ooh, where's that?
Underneath presentation.
Agreed? Yeah? 100% or 10% agreement? Yeah? Session is okay. Other layers from this side first, you guys. We have now. I wrote. Yeah, no one can read that, but I can tell you. So that's presentation. That session that we figured out already, and they kind of course, relate to the original, to this TCP model that we have here already. Transport, of course. Yeah. Where's that?
After session. Before.
Yeah, there, right, somewhere there. But okay. So below. So that's kind of quite straightforward because that's the same, right? So it exists in both models. Yeah. What else? Network, yeah. Yeah? Agreed, cool. That's confirmation on both sides. Yeah. Data link layer. And then?
Physical.
Physical, cool. All right, you guys on the same page. That's good. It's not 7 yet, is it? What am I missing?
One after session, but I can
No, it's just application.
There you go. And where is it? Where is last? There or there? There, okay. Right. Good. The actual application layer. So in the original ISO OC model, Open Systems Interconnect model, the application layer is on top and it's distinctively different from the presentation and the session layer, right? So those three ones are kind of combined. That's the tough bit if you want to learn that model. You just need to differentiate and keep the order right of those ones, because it's kind of a bit annoying. So I'm always thinking about it like from a practical point of view. This is what the user actually interacts with. This is what the layout is meant to be. I'm thinking about, for example, HTML is a good way. You're presenting something, but you're not defining the interaction, right? You're just giving a skeleton of what the user sees. And below that is the session protocol, which basically just keeps track of multiple interactions, right? It's not visible per se, but it just ensures that individual requests are considered as one continuous session. For example, if you browse through a web shop or whatever else, not something you actively see, but it's still infrastructurally important, right? So an application layer is what you actually see and do with the system, right? Like if, in a human-computer interaction sense. But again, they are kind of the equivalent to the application layer in the Department of Defense model. So cool. All right, so that took us about 8 minutes to get back where we were. Is everyone on board with this, the 7 layers of nothingness? Learn them by heart. Before you go to bed, recite them. Right? Stop the praying bit, use the ISO model. That's way more useful. So
Pray to the ISO model.
well, I'm not going as far. No, it's only one of many models, right? So it's only one of many models, but I think it's useful if you think about networking, right? So because all protocols will be structured in this kind of a similar way, right? So where you have this decomposition, and really helps you. And I promise you, it will help you when you go back to operating systems eventually and learn about the different structure there, because you can relate a lot to that. Okay. Good. So now we have the layers. And I talked about decomposition and different headers and so on. We figured out a lot of things, right? So the transport layer is responsible for services, right? The endpoints, the ports, network layer. What protocol was there again? IP, that's right. What does the IP protocol do?
To connect between two hosts.
That's right? So it operates on the host level, right? Transport layer operates on the port level, which is under the host. So, but I didn't say, was there? I don't want to swallow your comments. I didn't say really how the networking works. First of all, just to clarify some things, we will not go into detail in this on this one right now, but the different layers, of course, when you interact with this, and you guys said it before, every time there's some packet traveling from one side to the other of the, to a different host, right? So from a sending station to the receiving station, you guys should really press the buttons there. You see something as well. So you guys in the back can just do a gentle press on the monitors. Then they should switch on. You should see what everyone else sees here. Sorry, it's my intuition that there's a roundish button thing, and you probably need to press it 2.5 seconds, I guess, feeling wise, until the red light blinks at the bottom, and then it will take another half a minute, and then it will come on. All right. So So the point here is every time we're sending packages from station A to station B, they always go through all those 7 layers, right? Or 4 layers, or those layers anyway. They start from the application level and are broken down to a bit string representation in a way, and then I interpret it the very same way as you said, to be differentiated based on what kind of network protocol are you dealing with, what kind of application and service are you dealing with. Remember, you can run more than one service on a machine. And also, you can run more than one client on a machine, right? Because client need ports as well, right? So, and since that works, that means there needs to be a way of differentiating between your, Spotify client and your email client, right? So, on your browser, of course, and so on, right? So, and in order to interact with those layers, and for example, to do filtering on those layers and sending packages, there are different devices that operate on different layers, right? So, for example, we have at the lowest level, the physical layer is things like repeaters. What is repeaters?
Basically just gets the bits in an input port and just outputs it on all the other ports.
Yeah, you're alluding to a hub, right? So, to some extent. I'm more thinking about, no, you're not wrong at all. It is one of the things that the hub actually does, but more generically, think about it like an amplifier, right? So, if you think about in a Wi-Fi sense, there's often the problem with range, right? So we go out of range, you don't have connectivity, right? And the only thing you need to do is to reinforce the signal, right? The transmission signal. So basically, it operates purely on a physical level in just reading and resending the signals in a denoise or noise-free and amplified fashion, right? So it's just basically an amplifier in the widest sense, yeah. Picking up noise or signals and reinforcing them. So it doesn't do anything apart from, repeating the data it gets, right? Pretty much like you say in a way, right? So next higher level is then the bridge. Oh, what does the bridge do?
No idea.
No idea. Okay, right.
Always wondered.
Huh? You always wonder, right?
Yeah,
So
because I read some people use the bridge to use Tor in China or something, so to bypass.
okay.
They try to block the Tor in China, and some people use the bridge to kind of bypass it.
I think the metaphor bridge is used differently in that context, though. But your point, please.
Yeah,
It's a tough one.
It can sort packages based on MAC addresses.
That's right. So it separates so-called collision domains, right? So which is something we perhaps get to in a second. So that's a tricky one. And not like super relevant for you guys. That's really more on the networky side of the spectrum, but we get there. So the router, what does that do? And that's something you will need to remember. And we will try to sort that out in a second. So it's going to get a bit clearer picture of what's actually happening.
It calculates the route of a package from one host to the other.
Cool. Route of a package. That's scary, right? Isn't it? So.
The road.
Yeah, no, you said the right thing. We just didn't talk about it, so it's probably a bit of interesting terminology for some participants. But there's no surprise; it's called router, right? So perhaps that's related. I don't know. So and of course, on the highest level, that's the gateway. This is kind of a application level mechanism that is able to, for example, filter data on the application level, and it's usually a software-based or mixed hardware-software-based solution. For example, if you think about internet filtering. That filters based on content, right? So they're filtering out like abusive language or things like this. There was in companies they often run those filters live, and those of course need to inspect particular traffic, and usually particular application level protocols such as HTTP, right? They will not look for example into the FTP connection, right? Because there's just the binary flow of data. But if it's made for user presentation, then it's relevant, for example, for such a filtering solution. So they are working on specific protocols of the application level. So they don't filter all the traffic, but only traffic that is for whatever reason relevant. Content filtering is a classical application in this context. But we stay on this level, the router level, and get there and get a better understanding. Right. So to start that, we go back to the IP layer, network layer over there, right? So, and here's the header again, beautiful as it is. Yeah, okay. Well, you can argue about it. But anyway, the two most important components, of course, are the IP addresses, right? So we have source address and target address, right? Okay. What's the size of those addresses?
32 bits
32 bits. Okay.
in a IPv4.
Yep, that's cool. Yep. 32 bits. All right. Something like this, right? Cool. Sounds good. Good. 32 bits. So with 32 bits, how many endpoints can we address?
A bit more than 4 billion.
That's right. Did everyone get this? Everyone. So addresses are 32 bits, right? So in the IP layer, and we can, well, with 32 bits, we can have, since they are representing addresses, we can have about 4 point whatever billion unique identifiers. Yeah. So that's the idea. Is 4.3 billion unique identifiers enough for the average internet? Because we only have that one internet. It's probably not, right? So it's probably not. No. Okay, probably not. All right, let's agree it's not. We get there. All right, representations. Well, of course, when you get your internet address, you guys all have, sit behind a router or the like, and you most certainly have seen an IP address before. They usually don't look this way, right? Is there anyone who's really geeky enough to type in a IP address like this? No? Probably not. Good, sensible. Right. So the idea is that you kind of chop it up into bytes, right? Into 4 bytes, and convert them to a decimal representation to get your internet IP addresses. And then there's kind of a bit of dot separation as well. So you would read something like 172.16.0.0, right? Something you're probably more comfortable with, or 192.168.0.1, things like that, right? Cool. So that's the main thing. So this is how addresses are identified. So one of the challenges, of course, we have a bit of a capacity problem. 4.3 billion doesn't cut it in 2018, and not even in 2010. So it's really an issue. We get there. Is there another issue? Let's assume we don't have that capacity issue of 4.3 billion. What is another challenge there if we have those addresses?
It's hard to remember what website uses different numbers. So if we didn't have the DNS, or
Yeah.
it would be difficult.
Yeah, we get DNS, slightly different story, we get there. What I want to get at is more like, okay, we all want to be connected to the internet, right? So in order to be connected to the internet and participate, send a request and receive a response, you kind of need to be identifiable, right? So it's like in any other case, if you send a letter, for example, right, to 4.3 billion people, you kind of need to have a good return address in case one of those doesn't arrive, right? Kind of makes sense, right? So you can only participate if you get a public address. We figured out that 4.3 billion is a bit tricky to assign one to everyone, but what apart from that is actually really tricky, because those would be public addresses. So what's the tricky bit about it?
Like routing to that specific address, like finding
Yes.
the route.
Yes, that's right. That's again, you are 1.5 or 3.5 steps ahead. Yeah.
Finding an address that is unique to you.
Brilliant. Yeah, that's precisely the point. How do you administer that? I mean, come on, right? So, I mean, we're living in Norway. That's pretty good. So we all have the Fødselsnummer, which is unique. Yeah. But who assigns that? Myself. I mean, I should probably. It would be interesting. Probably get my birth date right then.
If I'm not mistaken, the state hospital.
Exactly. Well, the essence is it's one institution doing it, right?
Yeah.
Right. So it's centrally responsible for this. And with 4.3 billion unique IP addresses that are supposedly assigned, one for each of us or 2 of us. In fact, I have a laptop in this one, so I need 2 already. Cuts it in half. Not helpful. So get rid of one device is obviously one solution. But no, the challenging point I want to get here is how do you distribute that stuff? It's next to impossible, right? So, things change too fast, right? Okay. So in order to deal with this, the idea was, okay, how can we delegate the responsibility of assigning IP addresses? Because indeed they are centrally managed and assigned to some extent, but it's broken down to different layers. And that's part of the reason why the idea of subnetting was introduced. And the idea there is basically, let's take the IP address here, the same one as before, and chop it up. All right, so we chop it up. It doesn't need to be in the middle, we get to that in a second, but here for simplicity reasons, I just chop it up in the middle, and now we're declaring the left part of it, the network part, and the right part of it, the host part. All right, so, okay, what does that mean? Well, in fact, what does that mean? Is anyone keen in giving a go at elaborating? Else, I'll do it. Just go for it.
So basically,
Okay.
wherever you put your like this
Yeah,
line
yeah.
basically separates how many networks you can have in a for that specific like 32-bit address,
Yeah.
and how many hosts can be in that network.
Good, good. Same. Anything to add, or was it?
You can add like the ISP handles the network part, and then the host part is
That's right.
internal.
Perfect, right? So this way you can delegate. So you can manage. So you separate thinking. You're thinking now, okay, we have number of networks and we have number of hosts per network. By doing that, you can delegate responsibility for the networks to someone else. And that's precisely what's happening, right? So by chopping up this part and saying, okay, you're responsible for the network 172.16.0.0. And then this provider deals with everything on the right side, right? So it's, for Telenor, for example, right? So it doesn't need to be that central institution, right? So like the Jana ICANN, which is actually distributing the numbers anyway, right? So you don't need to phone to North America in order to figure out, okay, what's my next IP address if you want to sign up with your router to your internet connectivity. No, Telenor is doing it for you, right? So that's the key idea. So breaking it down, right? So, and then oftentimes when you see that notation, you get something, please come back. Okay. All right, you see it somewhere else. Oh, there you go. Oftentimes when you see that notation, you get something like, 172.16.0.0/16, right? And this basically just signifies, if you have the bit representation, how many bits are related to the network part. And of course, the remainder of the 32 bits is then related to the host part, right? What's the equivalent writing that you have probably seen more often? No one else? Okay, the networkers amongst us, please.
255.255.0.0.
Exactly, right? So the subnet mask usually, it's then, particularly if you use Windows, you configure there, then you would write something like this, right? You have a second entry, you have IP address here. This is not, okay, let's stick with this. And then you have a subnet mask below that you need to specify. And it does the same thing, right? So basically decimal representation of how many of those bits are related to the network part and how many of those bits are related to the host part, right? So, good. So we got the delegation bit going. That makes things a lot easier, right? So question now is, in this network here, for example, how many hosts could be in one network? Right? We figured out the left side is managed by Telenor and passed down to us. The right side is then, the left part is managed by Telenor, and then the hosts, all of the clients, they get one unique IP address. So how many clients can they have?
65,500.
That's correct, right? So 65,500. Quite a bit, but not really, right? So I mean, not for Telenor, I think. So that's right. So you're kind of constraining, of course, right? There's a bit of a trade-off, right? Do you want to have more networks and with fewer hosts, or fewer networks with more hosts, right? That's the key idea. And in this consequence, you can basically shift and move this the network part and the host part, for example, right? So in this case, how many hosts would we have left here?
154.
256.
Like one is used for like network address and one is for what's it called, broadcast.
That's right. So that's another. That's okay. So that's precisely right. So you have generally 200. We would say 256, but you remove two of them. Briefly, why is that the case? Well, the first address, which would be in our case 192.168.0.0, is technically not an IP address, right? So that's the so-called network address. It identifies the whole network. So that's not to be assigned, not to be used, right? So on the last one, which is 255, so it'd be something like this. So again, since the host part is only the last byte, only that one is modified, right? So you have the network address is 192.168.0.0. The first address is 192.168.0.1. Second address is .2, .3, blah, 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 blah. And the last one will be 255, right? Because we are zero based, so we end at 255. This is the so-called broadcast address. What does the broadcast address do?
It basically transmits that signal to all the
Yeah.
devices on it?
So that's kind of an old convention, challenged and abolished in IPv6. By IPv4 it still exists. If you send to that address, it means you send to everyone on that network. It's a good way of addressing everyone, right? So it's usually meant for administrative purposes, right? To share information with all hosts without bothering how many you actually have right now on the network. So those two ones are out, so therefore you are down to 254 address, whatever, right? So, but in practice, let's ignore that a bit. So that's a bit too networky, I guess. But just to get the intuition across why this is the case. Cool. So we have this variation, okay, between networks and hosts, and we figured out, okay, if we play with this. We can have either, 65K, for example. So what happens if we have a /8 network? 10 dot slash
2 to the power 24.
2 to the power. That's right. That's right. So if we do something like this /8, right? At 10.0.0.0 and /8. 2 to the power of 24. What's 2 to the power of 24? Ballpark. 16.7 million, right? Anyone check?
Yes, it's 16.7, well, 16.8 if you run that.
Yep, cool. So around there, right? So you see, by shifting the subnet mask, you have considerable changes. A lot fewer networks, but with a lot more possible hosts, right? So if you're in a, for example, you manage a company, you say, yeah, I need more than 65K of hosts. You better get a, network that has, for example, a /8 prefix and so on. But of course, this chopping up happens also in between, right? So you can, for example, eat into your host parts here and further separate different parts of your network into individual networks. So the idea here is that when you are, as an administrator, are passed down a particular network with your prefix, you can further subdivide it if you want to, right? But you're not to the left, only to the right, right? So you can say, well, actually, I only want to use 7 bits for network for host identification, but instead then have another, what is it? How many networks then? How many networks can I have with 1 bit?
2.
Yeah. So you basically you split your number of possible hosts in half, right? So you can do that further, right? By saying, okay, the first 2 bits are basically my network part that I manage. Getting 4 networks, cool. But it basically divides the number of possible hosts by 4 as well, right? So it's a kind of trade-off you're dealing with as an admin. So it's often quite nice to have it's desirable to have a low prefix handed down from the next higher provider, so you can do as much subdivision as possible on your own, right? So certain desirability. You get the essence there, right? Roughly. We're not configuring that stuff, but you need to understand what's going on. And one of the key issues is there that if you want your machines to communicate, and yes, we want the internet thing going on, so we kind of want our machines to communicate, direct communication will only work if they're sitting on the same network. So they need to be amongst this, in this host part, in terms of your addresses. So if hosts, for example, have 192.168.0.1 and 192.168.0.2 and .3 and so on, then they can all communicate, right? If your host has an IP address and it's part of this network, is 192.168.1.1, this one will not be able to communicate with the 0.1 host, right? Because it's sitting in a different network. They are separated. Yeah, they can't interact, at least not on an IP level, right? So they may be possibly able to interact on a physical level, if you like, but you will not be able to transport any package from A to B directly, right? So they can't be directly communicating. So there's a bit of a challenge there. And this is precisely a reason why we need those ones here, those router fellows. Their role is basically to route between those different networks. If something is differentiated in the network part and you want to have connectivity between different hosts from those networks, you need to have a router in between. Yeah, and that's something you commonly experience, of course, in your home, because if you have a Wi-Fi router, then this is basically dealing with this. Getting to that in a second. Right, this is the notation that you kind of know, just to reinforce it, prefix-based. I should have shown that slide earlier. So /16 is usually used by network admins and because router admins, because they kind of know what it means, and you guys now know as well. But oftentimes on Windows in particular, dealing with the subnet mask notation, is basically a decimal representation of the same thing. And in essence, it's basically the idea now of how to deal with the distribution of addresses is to actually chop them up in /8 blocks by default, right? So you have different blocks, /8 blocks that are handed down by the ICANN, which centrally manages all public IP addresses. Public, then there must be also private as well. I'll get to that as well. And this is then handed down to registrars that are usually regionally distributed, right? So they get those /8 packages, and then they further distribute them amongst participants and providers, and or if you're large enough, like Microsoft and so on, you can also directly approach your registrar and get local regional registrar and get IP address blocks as well. And the chop up is roughly like this here, right? So, yeah. So which region has the most IP addresses left, presumably, if any?
Right and CC perhaps.
Left. Meaning IP addresses they can still distribute. That's right? So Africa still has the most remaining IP addresses they can distribute because the demand is simply too high, right? Yes, North America and RIPE, they got amongst the most IP addresses, but they were snapped up like this. Asia Pacifica has a way higher demand than available IP addresses, and that quickly has led to extortion. So they are the fastest and the drivers of IPv6 because they don't have enough IPv4 addresses, right? So over there, so it's quite a bit of an issue. But there's quite a bit of distribution still going on in Africa. So if you're there, you have a fair chance of still getting IPv4 address for your organization or the like. Right? Cool. All right, this was a hypothetical example, just to run that through if you like. So if you, for example, University of Oslo gets that that kind of network and NTNU gets that network, they could, for example, subdivide it in this particular case, right? So in this particular way, right? So we figured out already this should be how many IP addresses here that Oslo would get theoretically. Yeah, to the power of 16 is?
65,000.
Cool. So 65,000, and NTNU would get the same. If we then subdivide this one, how many IP addresses would Trondheim get and Gjøvik get in that fashion? If we subdivide in that fashion, which is not clever, but that's a different story. That's right, right? So they have their 250 odd nodes each. So that's the idea. So if you give the central, administrative campus or so on a block of IP addresses, then they can subdivide it, and that obviously increases the number of network, but reduces the number of host addresses available, for example. So, all right. So we have this IPv4 addressing problem. So how many of you actually have public IP addresses at home? How many of you have a router at home? 1, 2, 3, 4, most of you. Cool. And the rest of one relies on SIP to do that for you, right? No?
Yeah, right now, yeah.
That's good. That's convenient, yes. Or NTNU, of course. Yeah, so that's the other challenge. So, of course, coming back to the 4.3 billion, we kind of exhausted them, right? So as I alluded to, there's hardly any capacity left. And see if I got a slide on that. I don't think I have. Yeah, so this is the extortion right now. So what is the remaining? So if you look at the different registrars, just to bring up that slide to give you a bit more context, a bit fairer. So we have the different registrars here. The Asia Pacifica is light blue, so they're pretty tough. Europe, okay, still quite there. But you see, the number of available IP addresses is rapidly going down. So Afrinex still has considerable set of pools, so they have nearly probably 7. What's the factor here? I don't know the factor right now. Consider at least the highest number of /8 prefixes still available for redistribution. Now it's going down rapidly, and most of the other ones at the end. So trajectory is by 2021, no new IP addresses anywhere on the planet anymore, right? So not even in Europe, not in Africa, nowhere else. Africa is still a bit of unknowns here, but Asia Pacifica is clearly running out. There's nothing more to distribute. So, but coming back, before we get to that challenge, one of the approaches of dealing with the lack of public IP addresses, because it's 4.3 billion, and evidently there's more than 4.3 billion devices on the planet, right? More than we use. You know, on average, probably we have even 2 kind of devices, and therefore IP addresses we kind of use, seemingly. But the way around it is to use private IP addresses. So there's a range, or ranges, in fact, of networks that are not to be used on the internet, not on the public internet. You can't use them, right? And it happens so that one of them is the IP, the network I just have used as an example all the time. It's actually not a valid IP address in a public sense. So you can't connect to the internet using this one. No one will talk to you, right? So, but they can use it in a private context. The idea is there, if you're running your own home network, for example, you can all use those ones, as long as you don't expose them to the public internet, right? So privately, you can all have your network with the network address 192.168.0.0, right? You, as long as you live in different places, right? If you live in the same place, you're on the same network anyway, so that's it, yeah. But point is, that's why you're probably more comfortable with some of those IP addresses, because they have been around for quite a bit, whether you're at your place, your parents' place, or your girlfriend's place, I don't know, right? So, but of course, there's more than this one. This is a /16 prefix, so we have 65K of addresses. But in some cases, if you have an organization, which I had at my time, was we had a 10.8 network because we needed more than 65K of distributable IP addresses. So we had a private network around the 10 point address, and then we basically had the subsidy, the different quarters of the different offices got their own networks respectively, right? 10.1, 10.2, 10.3. So it's very handy as a way of subdivision. So for you, if you are in that role, it's also wise to pick the right kind of private address to build up your IP range if you're running only an organization internal network. So, okay, so those are the private IPs, and they can't be used and can't be seen on the public network. Good. So, but what's the issue here?
So we use it for posts. It's
Yeah. So how do you communicate with the internet if you have?
it's counterintuitive.
Sorry.
It's counterintuitive because we say it's private IP address,
Yeah.
but if it's private, then we cannot communicate.
Yeah, that's
but
stupid, right? So it's like you have an organization-wide network. You have your kind of intranet network thing, right? So you can talk to each other. You send each other like text messages and so on. But internet browsing is not possible. That's a bit stupid, right? So they didn't think it through, did they? Of course they did, to some extent. So, but one of the way of dealing with those shortcomings, and that's my way of explaining you routing, is to use the idea of network address translation, right? So how does it work? So think about this as a network. So the left side is the inside network, organizational network. And we have 2 clients. Can be arbitrary more. So 192.168.1 and .2, right? And we have a router on the right side then, is the outside network, and that has IP addresses such as, 888, and some other IP addresses which actually don't matter for that matter. I just wanted to have diverse IP addresses that are valid public IP addresses. Now, every time, so how would the communication, by your intuition, how would the communication basically work in this kind of context? If, for example, client A wants to access www.google.com, what happens?
basically, Google doesn't receive that 192.168.1.1 address, but it just receives the external IP of the
Cool.
router.
All right, Yoko, you seem to know what's going on. Okay, so that was a practical example of network address translation. So what he said was, well, if client A, say, types www.google, or let's keep it simple, if the client A types this IP address, 216.24.78.2, right, then it will realize, oops, actually, I'm in the network 192.168.1/24. It realizes, okay, that's outside of my network, right? It can easily calculate it itself. If that's the case, it will contact the so-called default gateway if it doesn't know where to look for. So sorry, I have no clue what's happening here. I've got this IP address. I want to get my request somewhere, do something with this, and give me a response. And this is precisely where the router comes into play, because its task, you mentioned that before, to figure out how to reach to the target host, right? If in doubt, go to the standard gateway, Of course, what you can do in larger companies, you could have multiple routers, then you need to have a bit more refined configuration setup to tell the host to which router to actually go for which purpose. But in your home network, if you have that case, it will always go to your Wi-Fi, router, right? Which is kind of router and the Wi-Fi receiver at the same time, sender at the same time. And it will then connect, it basically will substitute the sender IP address, so which is 192.168.1.1 with its own external IP address, because the router is member of both networks. Both on the internal network, it has in this case has the IP address 192.168.1.254 and has the external address 175.17.2.88 assigned by Telenor, right? So that's something you don't manage. That's one of those addresses that comes down from the provider. And it will basically, when sending the package, you saw the IP package before, it has a destination and a source IP address. It will keep the destination IP address, but the router will change the source IP address to its own external one. So meaning when Google eventually responds, it will be redirected to the router's external interface again. And the router now needs to keep track of whom the request actually came from and then route it back to the internal host, meaning substitute the destination address when the packet reaches with the original requester's one again. So the package actually finds its way back to 192.168.1.1. That's so-called network address translation. This way, you can have an arbitrary large number of, in principle, arbitrary large number of hosts inside your network that all share one public IP address. Yeah. This way, that's kind of the not the original intent, because you lose the actual internet philosophy, which what each host has a public IP address, is directly able to communicate with everyone else, but at least everyone has internet access. Yeah. What's the downside of this approach? Let's ignore that. Not that it's wrong, it's right, but let's ignore that for this guy, because yeah, but you know.
Communicating internally and overlap with the outside.
Can you elaborate just to clarify?
Like, say you want to, like, say that the client B has an internal IP address that's the same as something externally that's also pretty much the same IP address.
That's something. So it could be another private network that of course has the same private IP address that could overlap, but it can't happen in the public area. So no one will have 192.168 in here, right? It would be yet another organization sitting behind its own router. But you're hitting to the right point, because
I'm not sure it's the right thing, but maybe that if you want the client A to communicate with the services directly, you're kind of behind the router, so you kind of have to port forward.
Nearly there. The other way around, right? So let's assume what happens, I rephrase your question, what happens if Google wants to actually talk to my client directly? Does that work?
So it has no idea.
It has no idea, right? It knows my public IP address, but there could be, you know, as far as I'm concerned, right now, 250 hosts behind it, right? So how do I know to which one to destinate it to, right? Because the host address is the IP address, right? And that's seemingly the host address. So in this case, there's the other way around. It's called, like exactly like you say, port forwarding. So in this case, this router or firewall, in this case pictured here, needs to do some sort of forwarding itself. So usually it operates based on port level. So if you get, for example, incoming requests to your network on port, let's say 80 HTTP or 443, which is HTTPS, or you know, or 25, which is the old-fashioned mail server port, then this router then would need to decide, okay, which of my internal hosts actually serves that, right, and redirects based on that host, so based on that port number. So if you get, for example, requests on port 80, you know, that needs to be forwarded to web server 192.168.0.5. But the outside party never sees that the service request is actually served by a server inside, but it always thinks that the router or firewall itself serves that request, right? So that's a very internal exercise. But of course, it still doesn't really allow it's not really flexible, because you can't just have multiple hosts listen on port 80. Well, there are ways around it, but point is, you can't just have address any of your hosts, you're always forced to redirect particular services. That's the key idea or limitation that you have. So it's kind of a bit of a truncated version of the internet idea, meaning there's no really free communication. There's a lot of configuration necessary, and you need to have control of that router. So you guys can't do port forwarding in NTNU, right? Because you don't control the access router that could say, well, actually, I want that, you know, port 80, please, NTNU, redirect port 80 onto my machine. No, they won't. I didn't try it, but I promise you they won't. If you try, let me know. I'll be interested about see about the response there. And that basically brings us to the capacity idea. So I hope you got the essence about the routing big to some extent, right? So the idea, if something sits outside your own network, meaning it's not within this network range identified by this prefix notation, then you need to have some sort of routing mechanism or gateway, as we call it commonly. Gateway is pretty much everything I don't know, which doesn't sit in my network, but I want to request something outside, send it to the default gateway, and then it deals with this. The reason I'm telling you this stuff is because we'll configure, or you will configure, an OpenStack instance, and you need to set up your own mini network. And to do that, you kind of need to bit understand, at least to that very extent, how the networking works, and then how do you assign IP addresses and what network addresses are, right? So that's the key idea here. So I encourage you to ask, but of course you can still do it later on as well. So I give you a bit of a break right now because I want to talk a bit about IPv6 because it's interesting to know. We won't use it, but for now, at least not explicitly, we may use it under the hood when we use AWS or the like, but we still need to talk about it a bit. So if you could be back here in 5 minutes perhaps, and then we can continue that briefly.